Okay.
Okay. Is on?
Yes. No, sorry. I pressed the button there.
Oh, I'm so bad with technology. Okay. Hello, everybody. Thank you for the invitation to Dr. DK Panda. And okay, this is the last talk. It's just a contribution talk because we didn't have much time to prepare a lot of stuff. And I will be really short. And I will talk about a sort of hobby for me because my official duty in Cambridge is not actually developing quantum espresso, something that I've been doing in the past and I became doing as a sort of fun. So I will talk about this GPUDirect approach for a parallel 3D-FFT. We already talked about weight case many times, so I will skip a lot of blah, blah, blah. But I will talk about a few funny facts at this point. First of all, we have 128 nodes in 16 racks, meaning that this is basically half of the system. The second part of the room is basically sandwich, and it's mirrored in the front. The reason is that when we procure the system, we decide for a scalable GPU cluster. We were heard about the GPUDirect technology. We say we want a system without constraint. So we went to procure and say we want specs such as we can leverage GPUDirect from every GPU at that time. Building came, blah, 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 came out with Dell. Therefore, was a solution that was a single cell was a 5U cell. But it was fitting our package, so we say, okay, that's cool. Then we realized that we need 2 IB cards to actually get GPUDirect over RDMA out of every GPU. And so we bought 2 connected cards. We put together the system, so every rack has 8 nodes. There are NVIDIA A20C, because since this is like a kind of workstation but flat, we cannot put the passive cooler, we have to put the active cold one, otherwise they put enough. And there is an InfiniBand switch on each rack, and then it's all connected to a central switch. Because we also have a A20C that is active cold, and because we also have a lot of airflow in the server, we manage during November 2013 to get the number 2 of the top green 500. And the reason is basically that the NVIDIA card do not overheat, because usually even during top HPR we don't go over 60 degrees of each card. And the airflow that comes from the doors on the back and on the cooling, it's very efficient. And some triggering on HPL parameter rollout with very nice score. The second funny part about the system is that the room, the entire room, not only the other cluster cooler target, is without, let's say, refrigerated cooling, meaning that the cooling comes from this back door with big fans that suck the air from the server and they cool down our back door. So basically, we don't have like a refrigerator in the room. We are able to cool down both of the systems, sandwich and GPU. In this way, each door apparently can take out almost 30 kilowatt of power in it. And it's very nice. We have the latest, it's not latest anymore because there is a new one, the latest NVIDIA driver, we have the latest MOFET, but we also have the magic fast copy kernel driver. So let's talk about the application then. Let's leave the system where it is. Quantum Espresso is an integrated software for basically for simulation of materials and nano-scale, and it's a free software. It's very famous. It's a huge diffusion in the open source community. There are also industry that use it. Why this is very special? It's very special because, like many other ab initio DFT code, you don't have a main kernel that does everything. And that is consumed like 80% of your whole time. There is linear algebra plus Lava Canyon solver. There is FFTs. Then you have grid operation. You have some sort of integration. There are many types of computational kernel. So how much is balanced between one type of, for example, Canyon solver or FFT? It really depends by the input. You change the input, and the behavior of the application can change radically. And I started actually because it's an ongoing project, a GPU porting of Quantum Espresso, one of the code in the suite, almost 2 years and a half ago. And we decided for design to leverage as much as possible libraries, from NVIDIA or maybe from third-party libraries, and to avoid massive change on the data distribution. There will be probably another talk talking about why we don't or why it should be a change in the data distribution. We didn't do this because since the code is open source and since there are many contributions coming from different sources, when you change something so deeply, you might break the work of someone else. And it's always complicated with a code that we don't have like a big organization that handles the entire development, and be sure that when you change something so radically, you break someone else's work. So most of the shared building blocks, the data distribution, we decide to keep it the same. So all those data distribution is based, like a lot of information called VASP, like Casper, like many others. It's based around this idea of distributing G-vectors. You basically describe your atomic system. And the number of G-vectors of your system can change based on many parameters, number of atom, type of potential. These vectors are not always the same length because of physical reasons. We don't go into detail. These different lengths, and they're distributed across the entire process in a sort of load balancing fashion. And because we consider a cube domain, but we apply a sort of approximation, such as we consider on a sphere within this domain, most of those G vectors have portions that are equal to 0 or fall out of the sphere, so we don't consider them at all. So they are not computed. And by having multiple G vectors, putting them together, we get, let's say, the elements of the supposed FFT that we want to compute. So, because there is this distribution, the way the 3D-FFT is handled is a kind of particular. We have sticks that are distributed not, let's say, contiguously, meaning that processor 0 doesn't have stick 0, stick 1, stick 2. We have stick 0, 33, 44, 90, 70, based on this length and this load balancing. And there are also several types of gradient. When you apply some operator, you may start with a small sphere, so a set of G vectors, and then expand. When you do the transposition, you might end up to set of planes or set of sticky, depending which side you're going. But you might have 0 elements that you don't compute. So we apply the 3D-FFT as basically, depending from which domain to the other. But the idea is that you start 1D, you apply an O2O, you apply a sort of parallel transposition, then you do a 2D batching, or vice versa. If you start from a domain, you start from 2D, you do a all-to-all parallel transposition and one FFT. Data distribution is something that we decided not to touch. So when we did the first, another particularity about this FFT is that we can more or less identify when this FFT is called mainly. The issue is how many FFT we call. By the nature of this problem, there is this HC routine that is basically applied to the user Hamiltonian FC, basically the basic set of wave function. And you have sort of iterating the process, meaning that for so-called non-convergent bands, you have a set of FFT that you can do potentially parallel. The point is that this number, during your iterative process, can start from 1,000 and arrive to 1. So sometimes you can potentially do 1,000 FFT, parallel FFT in parallel. Sometimes you just have to do 1. It doesn't really depend by the number of MPI, it really depends by the physical system. So what we did is a GPU porting, and where and why we failed. We did something very dumb. We had to start at some point. We basically took FFT, FFT, FFT from IBM, FFT from NK, whatever scalar driver for the FFT, we replace with the CUFFT version, and we keep the MPI as it is. And we start to look at what's going on. What was the problem? We realized that the GPU were actually too fast to process our FFT. That even if we have thousands of atoms, they are never bigger than 200 cube, 250 cube. We'll never see a system bigger than that. And we compute very fast, very short FFT, even batch of FFT, where the data transfer from host to device was always very kind of overlapping, always the main problem. So what kind of workaround could apply still without touching the distribution? We could apply some sort of task group strategy, something that comes from historical in this code, basically how to group some FFT to increase the level of computation, but still to group FFT that are distributed to apply more communication just to do this grouping. So still have to spend time communicating more. Or we can also think about that. 1D is too fast, 2D is still too fast. Why we don't group an entire 3D-FFT and batch it? The problem is that still, without touching that distribution, not only we have more computation, so potentially more speed up, but you still have to do more computation. By the way, in the serial implementation, we don't have this data distribution because there is no MPI model, there is no reordering of the GC, so we can call FFT straight away. The speed up of the serial, the potential speed up of the serial code is around 12x. So we can leverage very well memory bandwidth, we can leverage very well the GPU. Our main problem is really the communication. So we started a project with an NVIDIA Intel and that basically built this 3D-FFT design GPUDirect aware, meaning that there are many things calling in the new one. So when you enter this operator, this HPC, we did some work in initialization, but at some point we call the FFT driver. This FFT driver performs computation on the GPU. It performs some scatter, scatter with some reordering. Then it does the other computation on the when basically move from G to S space. And there are some reordering because you get a piece of the stick that you have to put in the right place on the plane. And then we call a word to word. And then we say, okay, we basically put a pointer to the device. Historically speaking, because I can anticipate this question, that was not a word to word, was a word to word. So 3 years ago, we used a word to word because different processor, different amount of speed. Then we say, after a while, okay, memory in the nodes is increasing, so who cares? We want some memory, but we do all to all. It's supposed to be much better than implementation. Perfectly fine. Because of that, we drop an implementation based on I send, I receive. It was made available at that time on the something like Infineon system. So all was still working well on some like IBM Federation type of network. For Infineon, but there were I send, I receive. So Infineon, even better. When we move forward, we drop the part. We then carry on the maintenance of that part. Now we can discuss if I send, I receive, that's actually something I'm working on, is better or not. So we put there, and they say, okay, fantastic. Now we have I say to myself, perfect. Now I have a system that can leverage the technology. I have an API library that can expose to these functionalities. I have the application. Let's see how the application works in principle. So this is still a proof of concept. The first thing that I did very naively was basically, let's see how it works. Okay. Not send and receive, because I don't use send and receive almost at all in my application. I want to see how it behaves with the MPI or tool. This is MVAPICH. This is the last one, the one that basically DK sent me like a Sunday morning. I'm in intro, send me mail, there's an MPI. Yes. I have to go in 2 hours. So I tried very naively just to give it a try. There is something very interesting. Naively means deploy the RPM, no optimization, nothing at all, just run it. There is this down at that message side, something that probably is possible to fix easily. And the GPUDirect copy, direct fast copy, that this new special feature start to, well, you gain something, you see third one compared to the second, it's not that much. I truly believe that for SLS16 it's much better. For all to all, straight away is not that nice. You start to lose something around 32 kilobytes. By the way, we probably, in my application, I already probably fall even further this message chat. It will depend by the input. So I tried my prototype. I call it prototype because I can easily break it since I know how to implement it. So not as rough as I did. So I used the previous one on the latest one because the system is busy. I use this system, but the this system is very small. I run FFT 75 cubes. We have just 200 non-converged electronic bandwidth in the first page. So there is a CPU implementation with 4 MPI. The GPU implementation, basically, yes, this is the GPU implementation. Is basically what it does. The GPU implementation is copy back, call the MPI or copy out to the GPU, and then I start to try to enable some of the features. So I keep the pointer, but just enable the put aware and enable the loopback, which is especially to stick the loopback, and the last one with the fast call. Now, it's not the persistent probably to this kind of method, because I have to try many of them, but at least it's promising in the sense that the last call is at least equal or slightly better then the one that actually physically copy few data back to the host and do the transfer. It's probably going to be different if I put MPI as send receiver. Or it may be even better if I actually increase the number of FFT batch. Just to give you an idea, this GPU validation handle 4 stream that basically take by themselves like a batch of FFT, and they do all the integrated FFT, and then they wait, they call them to all together, they start together the 2 FFT once you transpose. And because this is a small system, when you start this routine, you have just 10 FFTs to perform. So each of these, so it's not even not bars, but that's the system as is. So that's just a number. But what is interesting is actually that it's not worst. The past was really bad. So as I say, this is a still work in progress. We want to validate this design, meaning that we want to see how further we can push it. And we do that in the right hardware and the right software. Otherwise, there's no point to actually waste time doing some software development. And we want to extend to all cases, different limited change, different type of calculation. There's many different ways to call this within the code. And we want to try the fine-tuning, see what needs work in terms of hardware platform. And then, what is at least my view is that up to some certain scenario, I will handle the situation. Like, there's no enough FFT, I'll try to put some workaround. But if there is no ideal PCA topology, I will let those guys actually fix everything. And that's all.
Let's thank Seneca. Any questions?
Time.
Actually, I have a couple of actually questions and clarifications. So the GDR copy is typically applicable in the small message range.
Yeah.
So that is the reason why you don't see the benefits like once you go to the larger messages. The other question is, sometime back we had looked at quantum ESPRESSO. I was wondering if you ever thought of let's say using non-blocking collectives. So you have this all-to-one.
Okay. About the GDR copy, yes, indeed, but there's a reason why probably resume all the design. Because the word you put, I receive and I send is probably better. So yes, okay, we're probably going to change that since this is the way to go.
Sure.
About non-blocking. Yes, in principle, yes. I mean, okay. Let's put in the context of the quantum ESPRESSO people, the developers. Okay, people that develop the code most of the time are not paid to do that, so they do it for their own research, their own way. So most of the senior people care mostly about what kind of physics you get out of the package. Okay. Now, in those kind of application, you will never run, or you will unlikely run thousands of nodes. Unless you have a very weird, very big system, then someone can actually raise the hand and say, are we still into the density functional theory? I mean, we're still about the same kind of physics as such a big system. So it's an interesting exercise from a computer science perspective. Unfortunately, I say unfortunately because I don't care about the science. I don't care about science. This is a nice hobby. But from the main PI of the project, they are more focused on the science out of this package. And I personally understand what they aim to, and so something like that is always here. It's an idea, but implementing will be really hard.
Okay. Hard from the physics perspective or hard from the resources perspective?
Resources. You need human people doing actually the work. So, yes.
The one thing that you might want to tell the PI is that he might save about 50% of his SUs or core hours if he tried non-blocking methods.
It would be nice to try, yes, indeed.
Any other questions? If not, oh yeah, please.
Go to slide 9.
Slide 9. Yes.
What are units?
Defining. Oh, okay. So this is latency, 5%, and this is basically the message side.
5%.
Yes. Just very now.
If there are any other questions, let's thank the speaker.
homogeneities.
Okay, so I think we have come to the conclusion of all the